Hello everyone. The topic of this video is Introduction to the Solution of Nonlinear Equation. We will then discuss the bisection method. Many engineering analyses require the determination value of the variable x that satisfy this nonlinear equation. This value of the x that satisfy this equation are known as the root of these equations. The number of roots may be finite or infinite and may be real or complex, depending on the equations and the physical problems. How about the function f of x? The function f of x may or may not be available in explicit form. If it's available in an explicit form, it may be in the form of a general nonlinear equation or a polynomial or a transcendental. For this reason, finding the roots of the nonlinear equations for nonlinear by numerical method is very important. Some methods for finding approximate value of the roots of f of x are discussed in this chapter. The first method for finding the roots of the function is a graphical interpretation. The real roots of an equation can be interpreted graphically. However, the graphical interpretation is not possible if the roots are complex. The roots occur where the graph of f of x crosses or touches the x-axis. If the graph of f of x touches or coincides with the x-axis at point x1, it's indicated that the equation f of x has multiple roots at the x1. Let's look at these two figures. If you look at this figure, as you can see, this graph is touch the point -1, okay, and this is the -1, okay, is the multiple roots for this function. Also for these functions, okay, the function touch the x-axis at -1, and we can say the -1 as the multiple roots for these functions. How about these functions? As you can see in this graph, the f of x cross the x-axis at the different points, okay, and x1, x2, x3, and x4 as the simple roots for this equation. And again, by graphical interpretations, we cannot find the complex roots. For example, we have these functions, okay, and this function has 3 roots. We have a multiple roots or double roots, okay, at point 3, and we have a simple roots at point 5. If we draw the graph of these equations, okay, as you can see, the graph of this function is cross the x-axis at a point 5, okay, and this is a simple root, and the graph is touch the x1, okay, at point 3, and this is as a double root for this function. The next one, for another point for the graphical interpretations, in some cases, the equation of f of x can be split into 2 separate parts, and the 2 parts can be represented graphically. And the point of intersection of the 2 parts denotes the root of the equations. For example, look at these equations, this function. We have to find the roots of this function. We can write this equation as this format. x cubed equal 2x minus 1. And now we plot the graph of these two equations. Okay, this graph is for the function x cubed, and this line is showing the graph of this function 2x minus 1. The point of intersections between these two graphs indicate the roots of this function. Okay, and as you can see at the x1 and x2, these two functions, okay, intersect each other. Let's look at one engineering problems. The natural frequency of axial vibration of a bar that fixed at the one end and carrying a mass m at the other end are given by this equation. The omega is a natural frequency, L is the length of the beam, and C is found by this equation, the root of E over rho, E as a Young's modulus, the rho as a density, and another component is M, is the mass of the bar, and the A is a cross-section of area of the bar. We should find the first three natural frequency of the bar by using a graphical procedure, okay, for different ratio of different ratio between the mass of these objects and the mass of the bar when the value as a 0.1, 0.5, and 1. If we look at these equations, frequency equation, as you can see, omega LC is common for these two, for the left and right side. Okay, if we assume omega L over C as a x, okay, we can write the cotangent x equal, we can consider the m over m as a r equal r times x. Now we have two function, one of the function as a cotangent, another one as a line. And what is the slope of the r? Is a 0.1, 0.5, and 1. Now we are trying to draw these two functions. This is about the rx at different value, and this is about the graph of the cotangent x, okay, for three natural frequency. And these 9 points is showing the intersection of these three lines with these three graphs, okay? And this is the answer. For example, if we consider when the ratio of the m over n as a 0.1, what is the value? Is the 1.429, okay? The next one is 4.306, and the last one is 7.229. This table shows the first three natural frequency of the bar for different ratio and different value of the mass of the object over the mass of the bar. For graphical method, as a general, we can say graphical method can be used to find the roots of any equation except the complex root, but it has the following limitation. It requires extensive computations to plot the graph of f of x, and the roots found from the graphical method will be less accurate. In this lecture and the following ones, you will become familiar with four variables method for finding the roots of a function. Bisection method, fixed point iteration, Newton-Raphson method, and secant method. These four methods as iterative methods. First, we start by bisection method. Assume that the interval AB contains a simple root of the P for this function. Okay, again, we have this function, and as you can see, this function crosses the x-axis at the point P, and the point P as the roots of this function. Maybe one root or as a roots of these functions. And this interval brackets the roots. The first estimate of the root is the midpoint. We try to find the midpoint of this interval by a plus b over 2. We check the residual to see if that is the root. If the residual of the function at P1 at this midpoint is less than the tolerance, and again, the tolerance set by user, if less than the tolerance is meaning the P1 or this midpoint as the roots of this function, and you have and you stop the algorithm. If no, proceed to next bisection. There are two possible cases. The roots may be located to the left or in the right of the midpoint. For this reason, we use the signum functions to check the location of the roots, okay? And the signum function indicates the sign of the number, okay? And how we can apply? First, we find the sign of the function at A and P, okay? If the sign is negative, is meaning the roots located between A and P, like as this example. For example, the sign of the function at point A is negative, and the sign of the function at midpoint is positive. Okay, for this reason, the root is located between A and this midpoint. But if the sign function is positive, it's meaning the root located between the B and between the midpoint and B. For example, if we continue this graph, okay, the value of this graph at point P1 is a negative, and also for the A is a negative. Negative times negative is a positive. For this reason, when the sign function becomes positive, it's meaning the roots located between the midpoint and B. Now we have a new interval, and we repeat the step 1 and 2 until tolerance is met. For example, look at these functions, and for these problems, the tolerance for iterative convergence and residual is set as a 10 to the minus 4. And we are trying to find the roots of this function for the interval 2 to 4.5. Okay. This is the function f of x equal x cubed the tolerance for residual and iterative convergence is given as a 10 to the minus 4. The bracket is given as a 2 to 4.5. The first step, we have to check this bracket, is it this interval, is it contains the roots or not? How we can check it? The value, we should find the value of the function at point 2. The value of the function at point 2 is minus 4.5. Then we find the value of this function at 4.5. When we plug to the function, the value of the function at this point is 36.75. This is negative and this is positive. For this reason, we can say this interval contains a simple roots of these functions. Okay, this is 2, this is 4.5. The value at 2 is minus 4.5 for the y-axis and 36.75. If we are connecting these two values together, as you can see, the function or this graph cross the x-axis. For this reason, this is acceptable, but always we check with the sign of these two values. Okay, for the first iteration, first we compute midpoint. P1 equal A plus B over 2 is meaning 2 plus 4.5 over 2 is 3.25. How we can check this is as a roots of the function or not? Now we check the residual at the first midpoint. The value of the function at this point is meaning 3.25 is 3.234. Okay, and how about the tolerance for this problem? The tolerance for residual and iterative convergence for this problem is set up as a 10 to the minus 4. As you can see, this number is larger than the tolerance, okay? And we have to iterate the algorithm. This means we have to go to the second iteration. But before we go to the second iteration, we should check where root lies. Again, we are using the signum function between f of a and midpoint. What is the value? What is the sign of the function at the point 2 is a negative, and the sign of the function at point P or as a midpoint, as you can see, is positive. When the answer is negative, it's meaning the root is located between A and P. And if I draw it visually, okay, see, this is X, this is Y. When the X as a 2, and this is as a midpoint, 3.25, the value of the function at point 2 is minus 4.5, and at the midpoint is 3.234. If you are connecting these 2 points, as you can see, these graphs cross the x-axis, okay? And this is 4.5. For this reason, for the second iterations, okay, our new interval become 2 to 3.25. Okay, second iteration. This is the interval. Now we are trying to find the midpoint for this new interval. The midpoint is, as a P2, is 2 plus 3.25 over 2, and the answer is 2.625. This is the new midpoint. Now we have to check the residual and iterative convergence. For checking the residual, again, we plug this value in the equation. When we find the value of this polynomial function at this point, at this new midpoint, the value is minus 3.123. The absolute value for the residual of the second iteration is 3.123, and this is larger than the tolerance. Okay, it's meaning based on the residual, okay, this midpoint doesn't meet the tolerance, and this is not as a root. Also, we are going to check the iterative convergence. For iterative convergence, we are using P2 is meaning the midpoint for the second iteration minus the midpoint for the first iteration. And this is 2.625 minus, and the midpoint for the first iteration is 3.25. And this is the value. And again, this value is larger than the tolerance, okay? And this is, the P2 is not the root for this example. The next step, we should check again, check where roots lies, okay? Again, we apply the signum functions between the A and this midpoint. The A for this problem is 2, and the midpoint for second interval is 2.625. The sign of the function at A is negative, and the sign of the function at the P2 is negative. What's the meaning? It means negative times negative is positive, okay? And when this signum function is positive, it's meaning the root is located in the after the midpoint. If I draw it, see, this is our interval for the second iteration. This is 2, 3.25, and the midpoint is 2.625. The value of the function at point 2 is minus 4.5, and the value of the function at P2 or midpoint of this interval is minus 3.123. If we are connecting these 2 points together, as you can see, it doesn't cross the x-axis in this interval. But if I continue this graph, okay, the graph will intersect the x-axis in this interval. For this reason, P2 to 3.25 become as a new interval for the third iteration. Okay, for third iteration, the interval is 2.625 to 3.20. Now we are trying to find the midpoint for the third iteration. A plus B over 2. 2.625, 3.25 over 2. Now we check the residual of the function at this new midpoint, okay? And when we check the residual of the function at this midpoint, okay, is 0.658. And as you can see, this is larger than the tolerance of this problem, that is 10 to the minus 4. And how about the iterative convergence? Now we have P3 minus the midpoint for the second iteration is 2.9375 minus 2.625, that we can say approximately as a 0.330. Still, this is larger than the tolerance, okay? It's meaning we have go to the fourth iteration. Before go to the fourth iteration, we should set up a new bracket or new interval. How we can check or how we can find the new interval? Again, we are using the signum functions, okay, between A and midpoint. What is the point A for these iterations? For this iteration, this is as a A and this is as a B. Okay. The A, the value of the function at 2.625 and the value of the function at this midpoint. The sign of the function at A is positive, and for this point is negative, and for this point also negative. Negative times negative is positive. It's meaning the root is located after this midpoint. Let me draw it. This is the interval for the third iteration, 2.625, 3.25. And this is the midpoint for the third iteration. Again, this is the A and this is the new B for the third iterations. The value of the function at this point is minus 3.123, and the value of the function at P3 is minus 0.658. If we connecting this point together, as you can see, it doesn't cross the x-axis in this interval, okay? But if we are continuing, it will intersect the x-axis between the P3 and B. For this reason, for the fourth iteration, the new interval will be 2.99375 and 3.25. And then we repeat all of these steps. Find the midpoint, check the residual, and iterative convergence. Once the answer and the residual or iterative convergence less than the tolerance, it's meaning the answer as the roots of the function. Okay, you can see the solution of this example on a note, okay? And we will continue this process, okay? And this is about the coding. For the coding, as you can see, the P1 is about the midpoint. This is show the residual. The epsilon is talk about the tolerance that defined by user. And we check the signal functions. If is negative, the midpoint become as a B. Otherwise, the midpoint is considered as A. This is about iterative convergence, and we check the residual. If the residual is less than the tolerance, we stop the algorithm, okay? Sorry, for stop the algorithm, okay, we have two options. If the residual is less than the tolerance, okay, we can stop the algorithm, or if the iterative convergence less than the epsilon, that's the value is equal to the tolerance, and like as the epsilon for this specific problem, we can stop the algorithm. But if the algorithm is not converged to the roots, okay, and the algorithm become diverges, okay, after when the residual larger than 10 to the power 9, the algorithm will be break. Okay, for these problems, the first midpoint is 3.25, and we iterate this in the bisections method, and after 15 iterations, the residual for this function is still larger than 10 to the minus 4. But how about the iterative convergence is less than 5, minus 5. For this reason, we can stop the iterations, and this is as the one root of the function. Again, depends on the algorithm, okay? Um, for example, for this algorithm, okay, it's mentioned we should meet one of these criteria, residual or iterative convergence. But if we should check residual and but if both of the residual and iterative convergence less than the tolerance, it's meaning we should continue this iteration until both of the component is meaning residual and iterative convergence becomes less than 10 to the minus 4. Look at this example. We have these functions, okay, and this is the interval that is given 0 and 2. For the first part of the question, we have to check and is it acceptable bracket or no, okay, and how we can check it. We have to find the value of the function at 0 and 2, okay. At point 0, the value of the function will be -3, and at point 2, the value of the function is 1, okay. It's meaning negative and positive. It's meaning this bracket or this interval contains a simple roots of the function. After that, find the first estimate of the root. How we can find it? We should find the midpoint for this interval. 0 plus 2 over 2, the answer as a 1. And if we plug to these equations, okay, we can find the residual, and 1 to the 2 minus 3, the answer is -2, or we can say the residual is 2. And then we can find the next bracket by applying the signum function. The value of the function at point 0 is negative, and the sign of the function at point 0 is negative, and the sign of the function at the midpoint is negative. Negative times negative is positive. It's meaning the root is located after the midpoint. And the next bracket will be 1 to the 2. Okay. In the next slide, we are going to answer these two questions. How can we determine the error in the bisection method? The next question, how can we calculate the number of iterations needed to meet the tolerance provided by user? Okay. This is about, first we do the error analysis. The maximum error at the starting point is a difference between the two endpoints, is meaning A and B. If we assume that the root lies on the left side of the function, okay, and left side of the bracket, is meaning the error for the second iterations, okay, the maximum error at the second iteration become this part. And we can say this is the half of the error for the first step. As a general, the error at each iterations become half of the error from the previous step in the bisection method. And if we continue to find the error for the third iteration, we can say is half of the error for this part, okay? And if we are trying to rewrite based on the first error, okay, we have this. And this is as a general equations for error for any iteration at nth iteration. The error at nth iteration is found based on b minus a over 2 to the power n minus 1. Okay. At the nth bisections, the largest possible absolute error will be half of the error at the nth iterations because the p as a exact root. What is the p sub n is the midpoint at the nth iteration. Okay, this is the error at the nth iterations. Okay, and if we, for example, assume the error, the real root, okay, is located at these points. Okay, the largest or maximum absolute error, okay, become half of the error at the end iterations. Or maybe if the root is located at this point, again, same as before, okay, the maximum error or largest absolute error for the nth iterations become half of the error at nth iteration. And if we try to write the absolute error for nth iterations, okay, we have this equation. And from last slide, we find the error at nth iteration follows these equations. And the absolute error in the bisection method is equal or smaller than b minus a over 2n. This is about the absolute error. And if we have information about the tolerance for absolute error, this value is meaning the absolute error should be less than the tolerance. And if we are trying to find the number of iterative that we need, the number of iteration that we need, the bisection method meet the tolerance, okay? If we rearrange this equation as this format and take ln from both sides of these equations, we find this equation. And this equation is show the number of iterations that we need to find the roots for the function based on the bisection method. For example, the a for one example is given as a 2. The b is 4.5. The tolerance by user is set as a 10 to the minus 5. When we plug to this equation, the answer is 17.9, and we have to round up, okay? For the number of iteration, always we have to round up our numbers, okay? It's meaning we need 18 iterations that you can find the roots of the function by the bisection method within the given tolerance that for this problem is 10 to the minus 5. For example, look at this example. We have this function and this interval is given. The tolerance for this problem is 10 to the minus 5. How many bisections to reach the error tolerance? If we plug to these equations, okay, the answer of these problems based on this interval and this tolerance will be 17.61, and again we have to round up. For this reason the answer is 18. If you look at the problems, okay, this is the midpoint, the midpoint for the first iteration, and when we continue it, okay, after 18 iterations, the residual of the function become less than the 10 to the minus 5. But for example, if you don't round up this number, okay, and round down this number, it's meaning at iteration 17, what is the value of the residual? Still larger than 10 to the minus 5, okay? And this is not acceptable roots because it doesn't meet the criteria and it doesn't meet the tolerance. For this reason, the correct answer after 18 iterations, the residual less than the tolerance, and this is as the root, one of the roots of the function. Another definition that we have to know that, okay, if we can write the error in any iterative method as this format, the K is represent the order of convergence of the method, and the C is a constant that does not depend on N. What is the range of the K? And for example, if the value of the K is 1, the method has linear convergence. If the value of K between 1 and 2, the method has superlinear convergence. And if the value of the K as a 2, the method has quadratic convergence, and etc. Let's try to find the convergence of the bisections method, the order of convergence of the bisection method. The error in bisection method we can write as this format. Okay, the error for n plus 1 iteration, okay, is half of the error at nth iteration, because we learned that in the bisection method, the error at each iteration is half of the error from the previous iterations. For this reason, we can write half of the error at the nth iteration. This is the C for bisection method and as a half. How about the power of the error at nth iteration is 1. For this reason, we can say the bisection method has a linear convergence. This is the end of this lecture, and quiz 2 will cover lecture 3 and